For most instruments, there's some sort of vibration that is reinforced by a resonant cavity. These are some pipes from a pipe organ, and I'll blow in the pipe just to show you that the longer the pipe, the lower the note is going to be. Now, what would you expect if I closed the pipe? The note should get lower. Most humans can hear from 20 hertz to 20,000 hertz. Sounds below 20 hertz are called infrasound, and sounds above 20,000 are called ultrasound. I'm going to turn up the frequency because I want to show you that even though the amplitude is not going to be changing, the volume of the sound, which is related to the amplitude, is not going to be changing, you don't perceive all frequencies equally loud. The other thing that you should notice is that many people cannot hear all the way up to 20,000 hertz. I'll tell you when it cuts out for me. Notice that it's already sounding much quieter, but I haven't touched the volume yet. We're finally in the 10,000 plus territory. And right about here at 11.7, I can no longer hear this note. Now, I could keep this speaker on all day long and teach, but I'm sure it would drive my students crazy. So I'll keep working my way up. This is where a lot of students start to lose their ability to hear, is about 16,000 hertz. Some with young ears can hear further than that. All right, this part of the video is going to be pretty intense because we are talking about intensity, which is measured in watts per meter squared. Watts are units of power. So how much power is distributed over an area? Now, the formula for intensity for sound is the power of the source divided by 4 pi r squared, where r is how far away you are from the source of the sound. So if mother's saying time for dinner and you are 100 meters from mother, you would put 100 in for r. Okay, if you recognize that 4 pi r squared, that's because that is the surface area of a sphere. So if I am a source of sound, that sound is going to move out spherically. It's going to move up, it's going to move left, it's going to move right, it's going to move down, and in 3 dimensions, it's going to move out like a sphere. So you're not going to get all that sound. So that power is going to be distributed over the surface area of a sphere, which is why intensity is in watts per meter squared. All right, I want to impress you with your ears because the threshold intensity that your ears can hear, it's called I0, is 1 times 10 to the negative 12 watts per meter squared. You seem impressed. That is a really small number. That is a tiny, tiny, tiny fluctuation in pressure to get that power distributed over a meter squared. For example, the sun hits the earth with 240 watts per meter squared. It's like the sun has 4 60-watt light bulbs sitting on the corners of every square meter of the earth. Right? And that doesn't seem like that much power. I mean, it is, but 1 times 10 to the negative 12, that's way smaller, and our ears can perceive that. I say that this threshold of hearing is the sound of a mouse peeing on cotton. So when we perceive sounds, because we can hear things that are all the way up to a watt per meter squared or more, we don't perceive them by intensity. We actually perceive them logarithmically. So we had to come up with a logarithmic scale for decibels, which is the measure of sound volume. And that logarithmic scale, if you remember logs, says that if I go up 10 decibels, that means it's 10 times more intense. If something is 20 decibels more, that is 100 times more intense. 30 decibels, 1,000. Now the decibel actually, I think originally was called the bell, named after Alexander Graham Bell. But we times it by 10, so I think that's why they call it the decibel. 10 times the log of the ratio of however intense a sound is divided by the minimum intensity that we can hear, right? Not that you really need to worry about this equation, but it just shows you where the different decibels come from. So for example, if something is 120 decibels, that's called the threshold of pain. That is 1 watt per meter squared. You can see that that is 12 powers of 10 more intense than the faintest thing you can hear. Right here I have a decibel meter and I have it set on the high setting. So we're looking at the red numbers. So you can see I'm literally about a foot away from the phone and I'm getting some of my peaks to hit about 100 decibels. Right, I'm going to continue talking at the same volume, but I'm going to walk to the far end of the classroom so that I can get as far away and still be in the classroom as possible. And you can see the decibels that it's recording. So right now I'm standing as far away, I would say I'm somewhere around 10 meters from the phone, and you can see how the decibels are dropping off. As I come back towards the phone, you should see the decibels picking back up. Just so you can see about what it would take to hit the threshold of pain. If I were to talk as loud as I could, I'm not even able to hit 110 decibels. Here's a place where I could maybe hit 120 decibels. Okay, I have a few more topics about sound waves that I want to hit. And the first one is the Doppler effect, which is basically the only reason that you would probably watch NASCAR, because there's a time in NASCAR where they're going to put the little thing in the corner of the screen that says crank it up, and they'll open the microphones around the track, and you'll see the cars coming into the corners, and you'll hear their pitch climbing like and as each car passes the camera, that pitch is going to drop. That's because of the Doppler effect. The Doppler effect is a change, it's an apparent change in the pitch or the frequency of a sound wave because the source is moving or the observer's moving. Oftentimes, like in NASCAR, it's the source of the sound that's moving. And what's happening is the sound waves in front of that source are being squished. It's not a change in amplitude. So sometimes people say, oh, the Doppler effect means that something is getting louder when it's moving closer to you. No, that happens, but that is not the Doppler effect. We wouldn't need to name that some special effect because that's just obvious. The Doppler effect is about something getting higher in pitch as it approaches you and getting lower as it moves away from you. So I have this little toy that makes a horrible noise. And you can kind of see that as I whirl it towards the camera and away, you're seeing the Doppler effect. But I have this ball that I can put it in. So hopefully I'm going to get it in there and not have it come flying out and ruin my phone. So I'm going to try to throw the ball just over the phone so you can hear the Doppler effect as the ball approaches and passes the phone. It's kind of nice when that sound stops. All right, over here on the board, I'm going to try to explain to you what's going on by talking about throwing things in water. So this will represent, I think I might have a glare. Oh, perfect. This is going to represent a pebble that I've thrown into a pond. You can see how circular waves move out, and they kind of have a uniform wavelength or frequency. So if you were here swimming about in the water, these waves would be hitting you with a regular frequency, right? But let's say that instead of being a pebble, now the source of those waves, this is going to be good, is a duck swimming, right? Well, if the duck's moving, the waves in front of the duck are going to be squished, and the waves behind the duck are going to be more spread out. You've probably seen that pattern before. Well, a lot of times with a boat, you can actually catch the waves that you're making, right? And so we actually see something that looks more like a wake. That line right there is the wake, right? Some people call that a bow wave, or maybe it's pronounced bow wave. It's a two-dimensional wave that really shows that you're catching the waves you're producing, and so the waves are all stacked up along that line. Right? So this first example is just regular waves moving out. This is the Doppler effect, albeit in water, because the duck is producing these water waves and it's catching up to the waves it's producing. It hasn't caught them, but it's squishing them in front and spreading them out behind. So you would have a high frequency in front and a low behind. Right? This is a bow wave. Now, it's going to look the same, but I'm going to draw it in 3 dimensions with a jet. This will be a jet. And the jet is producing sound waves. Oh, kind of got off the screen there. This is high quality. The jet's producing sound waves, and those sound waves cannot outrun the jet because the jet is going what we call Mach 1. It's going as fast as the sound it's producing. There, make that bulb like that. So the jet has caught the sound. So it's not really hearing anything, the pilot of the jet. But we get this 3-dimensional cone. So it's just like the bow wave, but now it's in 3 dimensions. These are all spheres. I don't know if you could tell. And this is a 3-dimensional cone called a shock wave. Now we can learn some things from that cone's shape. For example, if you have a cone like this, and here's the jet right here, you know that the jet used to be right there at one point, and now the jet has traveled that far, and sound has traveled that far. So you can use those ratios to figure out the Mach number, how many times the speed of sound you're going. A lot of people think that as soon as the jet breaks the sound barrier, which is 343 meters per second or like 760 miles per hour, that everybody's going to hear a sonic boom. But you don't. Pilot's not hearing the sonic boom because the sound's all behind them. Really, it would only be somebody who's getting hit by this wake, so to speak, of sound. So even if you're right here and the jet's already gone past you, until that cone hits your ear, you don't hear the sonic boom.